So now let us continue with our discussion. So S2 is nothing but S1, but this S1 was nothing but SF plus X into SFG. And what is the temperature of this refrigerant at 1? It is minus 15 degrees Celsius. That is already given in the question. That is already we have marked in the TS diagram. T4 and T1 will be minus 15 degrees Celsius. Okay, so refer the tables of ammonia. Find out the SF value at minus 15 degrees Celsius. We may have to interpolate the values, so it will be 0.74235 at minus 15 degrees Celsius, and SG value again at minus 15 degrees Celsius will be 5.79915. Okay, but what is this SFG, or entropy of the vapor content at 0.1? That will be SG minus SF. Okay, so that will be this value, the difference of these values, and we will be arriving at 5.0568. So substituting this value here, and the only unknown term will be X, or Raynaud's fraction. We can solve this equation and find the Raynaud's fraction as 0.9. Or what does that mean? The condition of refrigerant at 0.1 will be 90% of vapor content, and only 10% will be liquid content. Okay, so we can substitute this value of X in our enthalpy relation. Already we have written the enthalpy relation to find the value of enthalpy at 0.1, that is HF plus X into HFG. So again we are substituting this value of X, Raynaud's fraction, to find out the value of H1. It will be HF plus X, which is nothing but 0.9 times HFG. What is the temperature at 0.1? It will be minus 15 degrees Celsius. So substituting all these values and solving the relation, we can find H1 as 1312.89 kilojoules per kilogram. Okay, so now we have found out both H1 and H2, and what will be the remaining? We have to find out the work done by the compressor. It will be nothing but H2 minus H1 times mass flow rate of the refrigerant. So substituting the values of H2 and H1 like this, times mass flow rate of the refrigerant, it will be 170.2 times mass flow rate of the refrigerant. So now till now we haven't found out the mass flow rate of the refrigerant. Now let us proceed to find the mass flow rate of the refrigerant. Okay, so in between, so how we can find the mass flow rate of the refrigerant? Anything, any idea is given in the question. So this ammonia refrigerator is producing 15 tons of ice from water at 0 degrees Celsius in a day. That is the idea. That is one idea given in the question. That till now we haven't utilized this idea. So what is this idea? It is this refrigerator is producing 15 tons of ice from water at 0 degrees Celsius in a day. So what does that mean? It is producing a refrigeration effect equivalent to production of 15 tons of ice from water at 0 degrees Celsius. And what is the duration of this process? It is in 1 day. Okay, so we can write this, or we can write that line in terms of refrigeration effect. So what is that refrigeration effect? RE, it is the production of 15 tons of ice from water at 0 degrees Celsius per day. Okay, so it this ice is produced from where? It is produced from ice at 0 degrees Celsius. So it is a phase transformation happening here. So we need to find out the latent heat, the total latent heat transfer happening in this conversion. That is conversion of water at 0 degrees Celsius to ice at 0 degrees Celsius. So here there is no sensible heat transfer, only latent heat transfer, because the water was also at 0 degrees Celsius initially and is producing ice also at 0 degrees Celsius. There is no temperature difference, only latent heat transfer is happening here. So that is why we can write this refrigeration effect as mass, the total mass of the ice or total mass of water involved, times the latent heat of fusion of ice or latent heat of melting of ice. Both are same. Okay, so latent heat of ice, it is already given 335 kilojoules per kilogram. What is the mass of the ice getting formed? It is 15 tons. 1 ton means 1000 kilogram. So 15 times 1000, this will be in kilogram, multiplied by 335 kilojoules per kilogram. Okay, and all this is happening per day. Per day means 1 day is having 24 hours, 1 hour is having 60 minutes, and 1 minute is having 60 seconds. So 24 into 60 into 60, so that will be in seconds. So finally the value will be in kilojoules per second, and that value is 58.15. Okay, but how we can relate this refrigeration effect with our mass flow rate of this refrigerant? So that is very easy. Already we have drawn the temperature entropy diagram and pressure enthalpy diagram. So when we look at this pressure enthalpy diagram, 4 to 1 was our refrigeration step, or the refrigeration effect is happening during 4 to 1. So also H1 minus H4 times mass flow rate of the refrigerant will be the refrigeration effect, and that is what we have found out just now. Okay, so H1 minus H4 into mass flow rate will be the total refrigeration effect, and that value we have found out. So refrigeration effect will be mass flow rate of the refrigerant times H1 minus H4. H1, okay, so H1 we have already found out. So what is H4? H4 is nothing but H4 will be nothing but H3. Why this is H4 will be becoming equal to H3? Because 3 to 4 is a constant enthalpy process, or H4 will be equal to H3 value. Okay, but what is this H3 value? It will be the HF, because why the refrigerant is becoming trisaturated liquid, it is becoming a saturated liquid when it is reaching the point 3, and point 3 is on the saturated liquid line. Okay, so H4 will be equal to H3, which will be nothing but HF value at which temperature? Temperature at 3 will be 25 degrees Celsius, and that we can find from the tables, and that will be 317.92, and we can now substitute the value of H4 as 317.92. The only unknown term here in this relation is mass flow rate of the refrigerant, and that is nothing but 0.058 kilogram per second. Okay, and straight away we can substitute this mass flow rate of the refrigerant in this relation, that is H2 minus H1 times mass flow rate, and we can straight away find the work done for the compressor. But wait, one more detail is given in the question. What is that? Assume actual COP is only 55% of the theoretical. Okay, so now we have to take care of this line also. Okay, that is, here in this case, this ammonia refrigerator, its actual COP is only 55% of the theoretical one. So now we have to find out what is the theoretical COP, then take that 55%. Okay, so now let us try to find out the theoretical COP. What is the theoretical COP? It is the refrigeration effect, or H1 minus H4 divided by the work done by the compressor, or H2 minus H1. All this H1, H4 and H2 we have already found out, and that is coming around 5.84. This is the theoretical COP. Okay, but what will be the actual COP? It will be only 55% of 5.84. that is nothing but 3.21. Okay, so how we can write that relation? Now what will be the actual COP? Actual COP will be actual refrigeration effect divided by the actual compressor work. Now this makes a sense. Okay, so what was this actual refrigeration effect? Actual refrigeration effect was this mass flow rate of the refrigerant times H1 minus H4, and we have already found the value as 58.15, and from this latent heat transfer producing 15 tons of ice from water at 0 degrees Celsius per day, and we have already found out the actual refrigeration effect, 58.15. Okay, so from this relation and the only unknown term here now will be work done, the actual work done by the compressor. We can cross multiply, and we can find the actual compressor work as 18.08 kilowatt. This will be the power required. Okay, so this is the end of our problem. Now all of you draw this temperature entropy diagram and pressure enthalpy diagram, and you have to practice using the data book also. So thank you.